Just
Please.
it's a, R prime is 5 ohms.
Alright, R prime.
Yeah.
We'll put it over here. R prime is usually per meter. 5 ohms per meter?
Yes.
Alright, go ahead.
And then L prime is 0.010 micro.
0.010 micro coulombs per meter. Go ahead. What is G? G?
G is 0.01.
And it's 1/1 meters. It's Siemens per meter. Go ahead. And what is C?
0.02.
Wait. This is C right here. Microcoulombs, you said?
No, it's supposed to be
It's supposed to be microhenries.
Is this supposed to be at microhenries?
Yeah.
Microhenries, and what is C?
0.02 nanofarads.
Per meter.
Yeah.
And they give you a frequency of 100 megahertz. What do they want? Gamma?
So find the voltage at the end of the line. At the end of the T line.
Help me out here, because now I'm a little uncertain what's given. Did they give a source resistance here or not? I'm not looking at it, so you have to help.
Yeah, 50.
50 ohms? Okay, this is 50. Go ahead. What else do they give
So
you?
they give you
I was just
ZL,
convinced
which
now.
is 50 minus J25.
They give you
They give you
voltage
the
at the
load.
load?
No, they give you ZL. They give you ZL.
ZL.
Okay. ZL is right here. Say that again, sir.
50 minus J25.
All right, go ahead.
And then the length of line is 1 meter.
All right. So 1 meter, go ahead. What do they want?
They want the
Find the
voltage.
voltage at each end of the T line.
Okay.
And they give you
Now, here's the problem. I'm trying to figure out this is information to get gamma and Z naught, all right? I want you to just listen to this, just for a second. This information, I'll be with you in a second. This information right here gives you gamma and Z naught. Do y'all hear me? If there's no Z naught, we need Z naught. I'll get that in 1 second, right? Now, after that, any other thing you want in terms of a voltage or anything like that has to be ascertained from a prior voltage given or current. Y'all with me on this, class? So I'll take a look at it now. But I want to tell you, this is one of those problems. I thought it was something else we were going to do. I thought it was just going to be a standard complete circuit problem. All right, let me take a look at this. Suppose a T-line at 2-13, and it's following it's okay, they give you that, we'll get that. If ZL is that, VS is, so it's 10 cosine ZS, and the length of the line is 1 meter, find the voltage at each end. This is 2.24. I think I did put 2. So probably 213. I just want to look at the circuit, make sure it isn't wild. All right, and they have. All right, they do that 50. Okay, I got it. This is an odd problem because he's going to have a lossy transmission line for the complete circuit, but it's very doable. So the first thing I'm going to do here, if you look at this right here, what we need is gamma. Y'all with me? And we need Z naught. All right, we need a characteristic of these. So we'll get there. First, we're going to say that we know that we have omega is 2 pi f, and f is 100 megahertz. So this is 2 pi times 10 to the 8 radians per second is going to be actually omega. Okay. Now after that we need gamma. So gamma is alpha plus j beta, and that's going to be the square root of r prime plus j omega l prime times g prime plus j omega c prime. These are calculations your calculator can do. It's plug and chug. They're given all the values at this point. Are you with me, class? We'll get to that in a second. We also need the characteristic impedance. And the characteristic impedance, actually, let me do this. This will work for a while. Characteristic impedance Now this is the characteristic impedance of the transmission line. It's not the input impedance. Are we clear on that, everyone? That's equal to the square root of R prime plus J omega L prime over G prime plus J omega C prime. You can give that to me. This one I'd prefer in real and imaginary terms, and this one I'd prefer, we can give it in the real and imaginary. Can you give me these values, please? If you have your calculators, just give it to me. How many tried this problem? The solutions are there, correct, class? And I really encourage you to do all the problems. If you miss some, you're probably going to miss some portion of understanding that's going to be critical. So I encourage you to do them all. Now, I did have a solution. I posted these, right? So, did you get these values? Anybody have the values for alpha and beta?
I can't see the originals.
For
What?
alpha, I got
Sorry.
2.23.
For what, alpha?
Yes, and for beta, I got
I'll put this down, but for...
Do you want this in? Well, I
No,
feel like
alpha is real. It's going to be real. So 2.23
And then beta would be 140.
plus J 140.
Yes.
Is that right, class?
I'm
Does anybody have the answer? Can you look at the solution and see if this confirms?
times 10 to the negative 6.
Both times 10 to the minus 6?
Just beta.
Beta?
Yeah, so I'm not really sure if that's correct. I think my calculator's wrong. But I did.
Something doesn't sound right. Can you check on that, guys? 10 to the minus 6 for me. That's like, this is 100 megahertz. There's no way. Can you give me this? So this is going to be alpha plus J beta, right? Just run the numbers. This is not a hard one. What do you get for alpha, anyway?
I think it's 0.2236. I might be wrong.
0.2236 plus J. Give me beta.
0.2810.
All right, I'm going to assume that's right. This is alpha, and this is beta. You all with me, class? Now, this is a lossy line. This is more complicated. I will not give you a lossy line for a quiz, but it's important. Some aspects of this you have to appreciate. Now, that's what's given for gamma. And what is Z naught, by the way?
It's 22.3607.
22.3607. What angle?
I don't see an angle.
Everybody confirm that? It could possibly not have an angle, but that is an oddity that you...
It doesn't.
Okay, that's by design. It's a rarity. You get a lossy transmission line without a characteristic impedance that has an angle. And it's because he on purpose defined R prime and G prime such that this would happen. Usually it doesn't if you have losses. Okay, so it's 22.3 ohms. Now, next thing we need is Zn right here. And this VOC, by the way, is 10 cosine, right? So I'm just going to go to the phase domain, 10 at 0 degrees volts. Does everybody understand the reason for that? The problem states 10 cosine of omega t with no phase in it. Just put 10 at an angle of 0 degrees. Correct, class? Now, we need the input impedance here first. We need Zn, and we need it so we can get this voltage V prime. That's what we need. So we got to get Zn. If you have calculators, get them out. This is going to be a different kind of calculation. So this is a complex impedance. Or, I'm sorry, this is a lossy transmission line. You can't use the standard calculation. You have to use the hyperbolic tan calculation. If somebody could look in your books and tell me where he gives you the general form that I'm about to put down, I'd appreciate it. So if it's a lossy line, then Zn is going to be equal to, and it will be Z naught. In this case, Z naught is real. But then it's going to be ZL. ZL is complex. Plus, and it's just going to be Z naught, but then it's the hyperbolic tangent of gamma. Gamma has both real and imaginary parts times L over Z naught plus ZL, the hyperbolic tangent of gamma L. Can anybody tell me where that is in the book? Now, some of your calculators may not have hyperbolic tangent.
It's page 51 in the book.
It's, she tells me it's on page 51. If you take a look at that. Can you all see that? How many have the hyperbolic tangent available on your calculators? I don't know. Most modern calculators have it or have a way to manipulate things so you can calculate the hyperbolic tangent. But the hyperbolic tangent has lost favor these days. Most of the times, anytime they do that, they use exponentials to define it. Did you? Yours does it? Just for, to speed things along, this calculation is doable. It is a lossy line, all right, and I'll level with you, I wish you should do it one time to appreciate the difficulty, but this is not something that real world people deal with a lot, because if you had a lossy line, you got a bad design. That's my opinion. Just, can you give me what Zn is getting on?
It's 27.2079.
27.2079 plus
Minus 15.4134.
minus
J.
J, 15?
Yeah, J, correct, yeah.
15 point what?
4134.
4134. And this would be in ohms. In the back you asked us, did you get that? Did you have hyperbolic tangent calculator? Did you do, let me ask you this, a real straightforward question. Did you do this calculation? Then you won't be able to get that unless you do this calculation. But it is a hyperbolic tangent, not TAN. Do you all hear me, class? All right, it's important to realize this is an odd problem, but it'll show you why things get irritatingly, you might say, long to calculate because of this. All right, we're going to assume we have that. Yes, sir.
So on that that lossy line equation, is there no J in front of that, like the 0 naught tan H?
The hyperbolic tangent takes care of this. Now,
Okay.
just last thing I'm going to say this. Suppose it was lossless. This equation will work. But then alpha will be 0, and you will have plus J beta. All right? If you take the tangent of J beta L, you get J tangent of beta L. That's what it defaults to. Follow me on this, class? The hyperbolic tangent accounts for the loss mechanism as well. All right, we get down to that. Let's assume we have this. Are you with me? I'm going to go through this. You with me on that? You asked it? Okay, now the next thing we need, if that is Zn, we need V prime. Everybody, what am I going to do to get V prime? That's just the voltage across here. If we replace the transmission line with that Zn, how do we get it? Well, we take this voltage, tan at an angle is 0 degrees, and we multiply it. You guys can do this on your calculators, by the Zn that we calculated, or looked up, in this case, looked up, over Zn plus Rs, or plus 50, right? So can anybody give me that? And I prefer it in terms of magnitude and angle, or magnitude and radian measurement. It doesn't matter either. Go ahead and do it. Now he's got the solutions up so he can actually look what Whitworth put down. Most of his answers are right. There's a few that aren't. Jeremiah, you got it? Anybody? Andrew? No? Anybody?
3.97 at an angle of negative 18 degrees.
3.97 an angle of minus 18 degrees. I'm just going to leave it as that. We could do that in radians. Do you all agree, class? We can put in terms of radians by multiplying by pi and divide by 180. I'm going to leave it as this for now. Do you all follow me, class? Why I'm doing what I'm doing. Now, what is V prime equal to? I'm going to have to make use of this stuff. And so much for my trend. All right, so for V prime, what happens? V prime is, if I wanted V0 plus, and I'm going to go right to V0 plus because we're a little low on time, that's V prime over e to the j, oh gosh, now it's lossy, so it's going to be, this is e, and this is going to be to the gamma L. Remember, gamma has a real and imaginary part. You all following this? It's not just j beta L, because it's a lossy line, so you have to put gamma, which has alpha. You with me, everyone, on this? You take that, and then you take plus the reflection coefficient below. We'll get that in a second. It's going to be times e to the minus gamma L. And now you're going to get the voltage V0 plus that we need. But before I say that, what is gamma L? How do you get gamma L? Fundamentally, you'll need to know this. It's the reflection coefficient at the load. You always look at the impedance you're going into, right? Hopping off the transmission line, which would be ZL minus the impedance you came from, which in this case is going to be Z naught. That is complex over ZL plus Z naught. Correct, class? Now, these are complex numbers. Can you give that? This is the calculation you need to do. Anybody? It'll have a magnitude equal to or less than 1. And it'll have a phase angle of something. I don't know what it is. Get out of here.
Oh, you want to tell it?
Might
Yeah,
as well.
it's 0.4479 minus J 0.1908.
Okay. All right, we can leave it in rectangular. It's fine. You all with me, class? Now take that number. I don't think we're going to have time to do this, but you all follow me. If we have this, we can get this. We've got V prime. Now you take e to the gamma L. Gamma has a real part alpha and an imaginary part J beta. You have to multiply the length of the line, and then you have to do this. The math is getting a little more complicated. I hope you appreciate that. That's how we did it in the book, in the solutions, right? Take a look. I guarantee you this. Follow me?
Sorry, 1 second. Yeah, it's
Are y'all with me, class? And remember, for the quiz, at least one empty chair between you and your neighbor. But for now, I don't care if you're sitting next to you. Go ahead.
yeah. You did it the same way you did.
Can you give me the answers of these?
It's 2.63 at an angle of 22, negative 22.
Minus 22 degrees?
Correct.
Now, at this point, what does he want? Voltage at the load, or what is he?
He wants voltage at the load.
All right. How many know what to do next? Don't tell me how to do it. If I have V0 plus, what's my next step to get voltage at the load? All right, I'm going to put down the equation here. And it's straightforward. Remember, we always put the load at Z equals 0. And my equation for V of Z is equal to V0 plus times what? E to the minus gamma, this is complex, so E to the minus gamma times Z plus the reflection coefficient at the load times E to the plus gamma times Z. Now this is the complex, this is for a lossy line. It's not either J beta now, you have to account for the loss. Y'all with me? But we're going to be at Z equals 0 for the voltage at the load. Does everybody agree with that? Yeah?
You swap the negatives on the gammas.
Well, what happens here? This is a forward-going wave, right? When we did this calculation, we were at Z equals minus L, weren't we?
Oh, okay, so you're
All right, so that's the reason for that. Down here, this is Z is minus L. Now, getting back to this thing, if you plug in the values, Z is 0, right? So that goes to 1, that goes to 1. That means the voltage at the load is nothing more than V0 plus times 1 plus gamma L. That'll be a complex number. Can you tell me what it says?
Yeah, it's 3.85 at an angle of negative 29.6.
29.6?
Correct.
All right, and I'm going to tell you, this problem is a little more complicated than it need be. But he's doing this to show you, sort of give you an idea of the level of difficulty of getting really a true lossy line, not a low lossy line. All right, the answer? All right, I wanted to do something with Smith chart before I just jump into the quiz. So, how many looked at the videos? All right, that woman does an excellent job, in my opinion. She's at Utah State, does an excellent job at discussing this in a very methodical way. I'm going to go ahead and assume at least most of you taken a look at this and you have Smith charts available. We're going to go ahead and show you how to work a Smith chart and how to get the values that are of importance for starters. The Smith chart are equations for trajectories related to the reflection coefficient of the line. get this, yeah. And let's see. Okay. So the way I like doing this is starting from very basic stuff. And this is what a Smith chart looks like. Probably going to have to ditch this marker. It's a big round circle. And it has a center point. And the points in the Smith chart that are of importance for starters. The first point is going to be this. And this is where r equals 1. It's a trajectory. And the second point is this. This is J1. And the third point, this, minus J1. They're at the northern and southern poles, you might say. And this will be 0. And this will have an infinite value. Now, if you have some charts in front of you, right? So what really happens is this, from the center plot to a point, is the reflection coefficient at the, yes sir, at the load, all right? It's the reflection coefficient at the load. Here's how we do this. I'm going to start by just showing you a diagram. This is by the way, Smith charts make life very easy. All the complex calculations we've been doing, these things do them that fast. And we're going to assume it has a characteristic of P of Z naught. And the first thing we want, well, we want everything, but we're going to come down to given length L, and what I want is Zn right here. Okay? This is a standard problem. Do you agree with this, class? All right. So the starting point of a Smith chart problem almost always is finding what's called the normalized impedance. And I'll tell you what, I won't even do the script. I'll just call it Z sub L, but it's normalized. So it's ZL, and that's the actual impedance of the load divided by Z naught. Now I'm going to put an example on so we can follow along. Let's assume that ZL here has a value of, say, 50 plus J20, okay? And I'm going to assume Z naught is 50 ohms. All right, so when we normalize this, we end up getting 50 plus J, 20 over 50, so I have 1 plus J, and it would be 2/5 or J 0.4. Can you all see that, class? Now take your Smith charts, and I want to make sure you see this. Take your Smith charts, and first find this trajectory. This is the one circle. The circle that is going to be about, what is it? I'm sorry, the real part of 1, never mind. You got that. Should have made it a little bigger. But when we look, who did this? So when we look at this, this is the one circle already, right? You all with me on that, class? Can you all see that? And there's J.4. Now watch this. This is important. These are trajectories. So if you come here, this is J1. J 0.4. There won't be a J here, but it's an assumed value. Anything that it pierces this thing orthogonally. And you'll see something like this here. Can you all see that in your thing? Now mark this point. This is point 1, and that is simply ZL. It's normalized value of ZL. This is not drawn to scale. Can you all see this? All right. Now draw a straight line from the center of the circle to this point, right here. The length of this is actually the magnitude of the reflection coefficient below. We'll get to that in 1 second. And you're going to see, if you extend this line out here, you're going to see something right on this edge that's going to have degrees. And you're going to see an angular measurement too. I want you to first do me a favor. Tell me the magnitude of this line from here to here when you measure it at the bottom. At the bottom of your Smith chart, you're going to have something that's going to have like RFL, I think. And you're going to see something where you can measure that distance, and that will have, if you take this length here and you go to the bottom of your Smith chart, just take a moment, and you look, you'll see something where it will give you the magnitude of that. Can you all see that, class? If you can see it, raise your hand. All right, what value do you get approximately? Anyone? We could get the exact value, couldn't we? If we wanted. Give me 1 second here. We can get the exact value. We could say it's ZL minus Z naught over ZL plus Z naught, correct? If we divide the top and bottom by Z naught, it would be normalized ZL minus 1 over normalized ZL plus 1. But you can get the exact value if you want. Do you agree, class? So what is the value you get for the reflection coefficient right here? In magnitude, just magnitude. Anyway. Point what? 0.2. About that? Anybody else get that? About 0.2? We can do that calculation, get it exactly, can't we? The magnitude? But it's about 0.2. And I don't know how close that is, but it's probably pretty good. This is a tougher problem because it's closer to the origin. All right, then some. Now, that's the first point, right? Now, you can get the angle here, right? What's the angle there? If you look, I forgot, but the angle is going to be measured 0 here all the way here. You're going to see angular measurements in degrees. Can you all see that? It's small print. Yeah. What did you get? 76 degrees?
75, 76.
So it's up, all right, we'll call it 76 degrees. So that means this reflection, this is about 76 degrees. Anybody else confirm that? Class? You got it? All right.
77.
All right. Now, all right, we're going to call it 76 for kicks. All right, and we're going to move on. Now, that is the angle. Now, I want you to listen very carefully to the next part. We got the magnitude of the reflection coefficient. If we wanted the standing wave ratio, there's 2 ways to get it. Which one way? Anyone? Standing wave ratio. 1 plus the magnitude of that thing, right? Of reflection coefficient over 1 minus the magnitude. You can do it that way. Or you can look on your Smith chart at the bottom, and you're going to see something that says SWR. They're going to be straight line graphs, and it'll say SWR. How many see that? You can just take that length that was associated with the reflection coefficient and put it down there, and you will see the standing wave ratio. And I don't even know, what is that? That's about 2.5, something like that. Anybody? What is the standing wave ratio? I don't know. What is it? Say again?
1.6.
Is it that low? 1.6? 1 plus 0.2 is 1.2. 1 minus 0.2 is 0.8. So 1.2 over 0.8, is that 1.6? Okay. Huh? We'll call it 1. I don't care. Y'all understand that, class? We'll move on. Now, this point right here that I'm showing you, I label it 0.1. Now, if we want to move and know the actual input impedance at any length away from the load, what we do is this. You've got a straight line out here. Pick your straight edge and move it. And there's going to be something out here that's got a labeling of wavelengths towards generator. Please locate that. So on the outer rim. And there will be a marking. These markings are in wavelengths. So I want you to look at that. Can you all see it? Now, can you tell me what the wavelengths towards generator is for this?
0.142.
All right. This is wavelengths. So this is 0.142. And it's assumed times lambda. I'm sorry, that's not a very good marker. And all right. So So this is 0.142, just listen to me now. 0.142, right there. Everybody with me? Now, we need to go ahead, think of this as a mile marker on a highway. You know what is it? There's exit 51 when you come off and come into Auburn, right? Off 65, or, yes. And if you take a look at that mile marker, 85, if you wanted to go 6 miles towards Atlanta, you would add 6 to that, right? So it'd be 51 plus 6 or 57, and you would come off on exit 57. You all following this? This is the same thing with the same principle. So think of this as a mile marker. If I want to, you're at the load, you can only go to the generator. If I want to go any distance, I'm going to pick a distance. Suppose I say I want to go a length of 0.25 land away, a quarter wave. So now I want to find out if I'm here, and by the way, I didn't say to do this, but go ahead and put a circle of radius gamma right there. You all with me? Now listen to me carefully here. So think of the mile marker. I'm at 0.142, but I want to go a quarter wavelength. So I want to find out where 0.142 plus 0.25 lambda is. What's that value? That's 0.392, isn't it, class? Now, if you look on the outer rim of this, just look with me, you're going to see something down here that's going to be 0.392. It's on the outer rim. Can everybody see that? How many can see this on your? Look carefully, by the way. You with me? Make a little, do a little thing here. 0.392 lambda. And then draw a straight line from the center of the circle through there. With me? Go ahead and take your time. I hope you have your compass and straight edge. Can you all see it in the far back too? Everybody. All right, now do this. You see where this line, the straight line, intersects that circle of constant radius? Tell me what value you have, because that is the normalized impedance at the input right there. This would be your Zn normalized. Can you tell me what it is? Now here's what you need to do. The real part right here will have the trajectories like, and I can't drum very well, but it's going to go like this. So there's going to be a circle like this that's symmetric above the actual equator, and there's going to be a part to that that's real. And what is the real part, anyone? Take a look at your switch chart. Please find it. I just need find this point, and then find what the value is of that circle that's going to go this way.
0.85.
All right, is that right, class? Anyone? You got that? How many got that? All right, now what's the imaginary component? The way you get the imaginary is you look for the line that's closest to going right through here and perpendicular to the edge. You're going to see a value here. What did you get?
J 0.35.
And it would be minus, because it's below the equator. So this right here would be minus J1. Say it again.
0.35.
Can you all see that? How many see that? You don't see it over there, or do you? Can you see it or not over there, guys? Yes? If you can, raise your hands over there. I need to know if you can or not. Some of you got it? Everybody got it back there too. All right? Now, if you want the actual, yes?
Could you look at that last step again?
You know how we got here, right?
0.85, right? We get that.
This is the real part, right?
Real part, right.
All right, find the circle like this that goes through that point and see what the value is. Jeremiah, can you show? Do you understand? All right, it should, now, admittedly, you've got to sometimes just, you have to approximate the value because the line doesn't go right through that point. But you should see something with a radius of about, this is going to be a trajectory this way of about 0.85. Can you all see it? Anybody not seeing it need a little help? You're not seeing it? Give me a show. Are you seeing it? You're not seeing it either? Are you seeing it? God. All right, you're seeing it. Go show her. It's the only way to do this. Andrew, you know what's going on, right? Anybody not see it? Do you see it? Do you see it? I'm afraid.
Did you write anything on it?
It's the only way to get this down is do it in class. You all see it? You see it? Down.
Are you following? Because I
Yay.
lost him at
Get up and show them how to do it.
I got lost before the 0.392.
Okay, I lost you at J6.4.
What?
I'm sorry, I lost you at J6.4.
All right. Look at the line that goes through it and comes here. All right. There's a trajectory that goes through it and comes here. Through that point.
See, like, the issue I'm having here is like,
Huh?
the problem I'm having here is like,
Sorry, I can't.
the problem I'm having is taking what you're writing on the board and applying it to what the ones you're taking.
Show me the Smith chart you do.
Yeah, so
Here, look. This, all right, the Smith chart is start like this. Is this it? Where's your, okay, there's your compass, right? Where's the, did you draw your line out? What is it, 0.392? So 0.392 is, there's 0.37, 0.392 is right here. See that? There's point, all right, now do this straight edge.
straight edge I have, so,
Bring your straight edge all the time. So you go from the center here and go right through and you get to do this. Now, see this point? That point right here. Here's a circle that's close. It's 0.6. This is, that's point, is that 0.8?
yeah, that's 0.7.
So this is 0.7. This looks like it's 0.7 something on yours. I don't know if I drew the point right. And if you drew the load, well, you didn't draw it. The load point's down here. Look, it comes in and it's got a value of 1 plus J.4, right? Here's the 1 circle, so it's on here, but J.4 is here. So that means this is the point. You drew the wrong circle. Now you've got to make a circle like that.
I'm gonna use my chart. Thank you.
Guys, are you guys getting it or not? How many have it? Got it. Far back, you guys? Over here? You guys there? Are you guys okay right here? You got it or not?
Just look like straight edge.
All right. If you want the value of the input impedance, the only thing to do is multiply the normalized value of Zn, which we have as, what the heck is it? What is it? 0.85 minus J.35. You all see that? 0.85 minus J.35 by the characteristic impedance, which is 50. Now you have the input impedance. You all with me, class? We're running out of time here because I got to give you your quiz. I'm going to pick it up from there, but I'm going to tell you, most of these problems, if you listen to me, bring your equipment, straight edge, compass, and some good Smith charts, you can go through these things in no time and you'll feel comfortable. But I warn you, you miss a couple of lectures of this, you're going to be grasping at straws. This is a weird thing because we're going to do matching. We're going to use this thing to basically solve all the problems we really can't solve easily with a calculator. So now, would you separate yourself? Make sure you have at least one empty desk between you and your neighbor, and everything off your desk except your phone. Take your phone and turn it down upside down. Turn it off on the desk. And if you have any watches, like a Google Watch, an Apple Watch, take them off and put them on the desk. You can't use anything like that. And I gave you the equation for input impedance. I want you to make sure you get at least the space between you and your neighbor. I'm going to start at the back. I may move people around and do that machine. Take no offense. Do me one favor, put your name on first.
Yeah, bro. saxophone playing right now, actually.
Yeah. That's great to be able to sing that as well.
I'm coming. I'll be right there.
Should I turn the computer off?
Yeah.
Go Marshall.